All right, in this video, we are going to talk about cube root transformations and key attributes. Okay, so the cube root parent function is the cube root of x. You are going to recognize that it is cube root because you will see a 3 in the index of the radical. And so a cube root essentially uncubes numbers. And so as we pick some significant points, we are going to want to pick input values that are perfect cubes. And so when I take the cube root of 8, you're asking yourself what number cubed would have given you 8. So because 2 cubed would have given me 8, that means the cube root of 8 is 2. And so we know the cube root of 1 is 1 because 1 cubed would have given me 1. Cube root of 0 is 0 because 0 cubed would have given me 0. And the cube root of -1 is -1 because -1 cubed gives me -1. And the cube root of -8 is -2 because -2 cubed would give me -8. So it's always kind of jarring to see that you can take the cube root of a negative number because we know we can't take the square root of a negative number and get a real value. But for cube root, you can. And so that's an important distinction between cube root and square root, is that we can have negative x values for our cube root. And so when we graph this function, we have the point 0, 0, 1, 1, and -1, -1. So the 2 points on each side, this forms a line, okay? Our graph is not linear, so we're not going to connect them with a line, but that's an important pattern to notice. And then we have the point 8, 2, and -8, -2. And so this function kind of looks like square root to the right, opening up to the right, but then we have the negative values to the left. So it's kind of like a reflected upside down square root pointing to the left. And so this point in the middle where it's going from concave right to concave left, that's called an inflection point. Anytime you're changing concavity, that's called inflection. Okay, and so for the parent function, the inflection point is 0, 0, but when we start translating our graph left, right, up, and down, that will change. Okay, and so right now our x-intercept is 0, 0, because that is where it's crossing the x-axis. And anytime 0 is your x-intercept, it's also your y-intercept, because that's where it's crossing the y-axis. And then as for the symmetry, you can tell this function doesn't have an axis of symmetry, because if I reflect it, it would be facing the opposite direction. But if I rotate this graph, it does look the same. And so this graph has rotational symmetry about that center point 0, 0. So anytime you have rotational symmetry, you're going to have a point of symmetry rather than an axis of symmetry. Axis is for reflections. Point of symmetry is for rotational symmetry. And then our domain and range are actually really easy because this function behaves much like a line. It's going forever to the right and forever to the left. So our domain is -infinity to +infinity. And then it is also going down forever and up forever. And so our range is also -infinity to +infinity. And so for square root, that is not the case, but for cube root, we will have all real numbers all the time. And so just be careful because you're going to be assessed on both. And so as soon as you see that cube root, that's when you have all real numbers for your domain and range. Okay, and so because our range is going from -infinity to +infinity, we also don't have a global max or min. Later, we are going to restrict our domain to be between two x values and then find max and min, and so that's when we will be able to get some values. Okay, and so here's a review of our transformation form, remembering that the a value gives us our vertical stretch and vertical compression, as well as our vertical reflection across the x-axis. The B value, because it's under the radical, everything's horizontal. And so our horizontal stretch, horizontal compression, and then our horizontal reflection across the y-axis. The H value underneath the radical is still in the horizontal direction, but that's our translations. And so that's right and left. And then the K value outside the radical will be the up and down because it's going to be a vertical change. Okay, and so you can kind of treat this like vertex form. HK, if we move right H up K, that's going to be our new inflection point. We started at 0, 0. For the parent function, and so shifting left, right, up, and down, that's going to change our inflection point to whatever those values are. And so remember, the inflection point is also the point of symmetry, and so we could ask for either of those things, and it's referring to the exact same point. Okay, and so we're going to practice graphing these. And so first thing you want to do is identify the transformations. So I'm seeing a +6 under the radical, and then a +1 outside the radical. And so that is a left 6 and then an up 1. Okay, and so that's going to move my inflection point. I'm going to call that IP. Left 6, up 1, so -6, 1. And so you could either start by graphing it there. I'm going to show you by graphing the parent function just so I can show you the pattern of the points. And so this says graph with at least 3 good points. And so I'll show you the important 3 and then how to get some extra points. So for our parent function, we have 1, 1, 8, 2. And then we have the -1, -1, -8, -2. Okay, and so if we shift left and shift right, the pattern between the points should be the same, or shift left and shift up. We are still going to have the same pattern. Okay, so we're going to take our inflection point left 6, up 1. Okay, and so if you had just started by graphing the inflection point, you would get your point on each side by following the slope of 1, up 1 over 1, and then we can go back 1 to get that slope. To get the other points on the ends, you would go up 1 over 7, and in this case down 1 still over 7. So the pattern is 1 then 7 for those horizontal distances. But if you just need 3, just graph the 2 on each side of the inflection point and make sure you are concave right, concave left. Okay, domain and range, all real numbers all the time. Okay, and for this next one, we have several transformations. We have a negative outside, and then we have a scale factor of 2. So that's going to be our reflection across the x-axis, and then our vertical stretch by 2. And then we have a -3 under the radical, that's right 3. Remember, everything under the radical is going to be opposite of what you would expect. Everything outside is what you would expect. So this -4 outside moves you down 4. Okay, and so starting with the fact that the inflection point is right 3 down 4, I'm going to go ahead and graph that at 3, -4. Okay, and then to get the other points, if there was no stretch and compression, I would just have my slope of 1, concave right, concave left. But we do have a reflection, and so that reflection is going to change our slope to a negative slope. If I just had a reflection, I would have a -1 slope, but you can kind of treat this scale factor, including the negative, as your new slope. Okay, and so when I graph my points, I'm going to have a -2 slope around the inflection point. So graph your inflection point, and then a slope of -2 would go down to right 1, up 2, back 1. And so don't graph it as a line. You're going to go concave left and then concave right. Okay, once again, negative infinity to positive infinity for the domain and range. And so when you're using your reflection and your scale factor, that's true even if your scale factor is inside the radical. You still treat it as your new slope. Okay, for this next few examples, we are going to talk about how to find intercepts and then max and min on given intervals. I'm going to skip the first example and just jump to example 3. So the first thing we want to do is identify our transformations. So we have our reflection across the x-axis. We have our vertical stretch by 4. And then we have our down 7. Notice that minus 7 is completely outside the radical. The radical ends at the x. So we aren't shifting left or right, just down 7. So if I were to sketch my graph, the inflection point would be down at negative 7. And then I know I would have a negative 4 for the slope. So I can go down 4, right 1. That's going to be a very steep slope. And so concave left and concave right. So the point of symmetry is 0, negative 7. Domain and range, all real numbers all the time. And then to find the max and min on the interval 2 to 6, remember these are x values, x equals 2 and x equals 6, and we're going to look between those two values. So we have 1, 2, 3, 4, 5, 6. We're looking between x equals 2 and x equals 6. So it's important to notice that you have a negative slope now. This is a decreasing function. So because it is decreasing, my max is actually going to occur at my left side, and then my minimum is going to occur at the right side. It's a subtle difference, but it's important to notice that, because if I'm just asking for the max, you're just going to plug in the x equals 2. If I'm asking for the min, you're just going to plug in the x equals 6. Of course, you could plug them both in and just see which number is larger, but even that difference is kind of subtle. And so I'm going to plug each of these values into my original equation, which has a negative 4 cube root of x minus 7. Negative 4 cube root of x minus 7. And so we're plugging in x equals 2, and then we're going to plug in x equals 6. Okay, and so these aren't, 2 is not a perfect cube, so these are not going to be nice numbers. And so if you have a calculator, you can get the decimal approximation. And so to type in a cube root into your calculator, that is the option math 4. Math 4. So I'm going to type in negative 4, then math 4 for the cube root, 2, use your arrow to get out of the radical, then minus 7. Okay, and so that is approximately negative 12.04. And then to do the second one, negative 4, math 4, type your 6, get out of the radical, then your minus 7. So that is negative 14.27. Okay, and so clearly our maximum, negative 12, is bigger than our minimum, which is negative 14. And so always check for that. Okay, and so for the max, your answer is negative 12.04. For the minimum, negative 14.27. Okay, for this next one, notice we do not have parentheses to separate our b value from our h value. If you look up here, the proper form, if you have a b, you need to have a set of parentheses to see what is being added or subtracted from x. Okay, and so my first step for this problem is to add those parentheses to factor out the 1/2. And so I divide that 2 by 1/2. And so in proper form, I would see a 1/2 parenthesis x minus 4. 2 divided by 1/2 is the same as multiplying by 2. And then, of course, if I were to distribute that back in, you would see I would get that 2 right back. Okay, and so these are algebraically equivalent, so that means their graphs are equivalent. If you were to type this first equation into a calculator, you would see that it is actually moved right 4. There's no way to see that by looking at this 2, so be very careful and make sure you have proper form. Okay, and so to identify the rest of the transformations, we have a reflection across the x-axis. And then this scale factor inside is a 1/2, and so that's actually a horizontal stretch by 2. That's still going to change our slope to a 1/2 if you were graphing this accurately. And then lastly, we have a right 4. Okay, and so for my graph, it hasn't moved up or down, so that puts our inflection point just at 4, 0. And then our new slope is negative 1/2. And so we would have up 1 over 2, down 1 back 2. Again, it doesn't have to be perfect for these. You just need to see that it's decreasing. So concave left, concave right. Okay, so it is a decreasing function. My point of symmetry is 4, 0. Domain and range is all real numbers all the time. And this time, my interval is going from x equals 0 to x equals 8. So starting at 0 and going to 8, it's really obvious that our maximum is occurring at the 0 and our minimum would be occurring at the 8. So if the question is asking for the max, you're plugging in the x equals 0. The min, you're plugging in x equals 8. Of course, you could plug them both in and just see which number is bigger, but I'd rather just plug in one. So here we're finding both. So taking my original equation, you can use the one that I've edited, but I prefer to use less parentheses. And so I am going to use this top equation. The only real reason you would need the parentheses is to identify transformations. As far as using the function, I prefer the one without. Okay, so negative cube root of 1/2 times x minus 2. That minus 2 is under the radical, so be careful. Okay, so negative cube root of 1/2 x minus 2. We're plugging in 0, and we're plugging in 8. So negative cube root, 1/2 of 0 is 0. And then we subtract 2, we get a negative 2. Now we have a negative outside and a negative inside. So leave them both, because when we type them in the calculator, you do see that we're going to end up with a negative times a negative. But in general, those wouldn't cancel. Here we have negative cube root, 1/2 of 8 is 4, subtract 2. So we get negative cube root of positive 2. Okay, and so to get the decimal approximation, we would type in the negative math 4, and then for the cube root of negative 2, we get 1.26. And then for the second one, negative math 4, cube root of positive 2, we get negative 1.26. Okay, so once again, our max is bigger than our min. It should be that way. And so your answer for the max is 1.26. Your answer for the minimum is negative 1.26. All right, in these next examples, we are going to find the x and y intercepts. So remember, for the x-intercept, you are plugging in y equals 0, for the y-intercept, you are plugging in x equals 0. Okay, so I'm going to start with the y-intercept because that's usually the easier one because you just number crunch. And so for the y-intercept, you're plugging in x equals 0. So I'd replace this x with 0, and I would get cube root of 4 minus 3. Of course, 4 isn't a perfect cube, so that is going to be a decimal approximation. But without a calculator, you would just leave it in terms of cube root. So I'm going to leave it for the sake of time. So cube root of 4 and then minus 3 outside for my y-intercept. Okay, let's go ahead and do example 6. Okay, so once again, for the y-intercept, you plug in 0 for the x. And so y equals the cube root of negative 0 minus 3 is negative 3, and then a plus 4. Don't lose that first negative, because then the negative cancels, and so I just have cube root of positive 3 plus 4. So 0 cube root of positive 3, and then a plus 4. If that 3 were a perfect cube, I would not leave it in terms of cube root, and so just double check that. Okay, for the x-intercept, that's a little bit harder because we're plugging in 0 for the y. And so that means the entire equation is equal to 0, and we have to solve for x. So that leaves me with cube root of x plus 4 minus 3 equals 0. First step to solving this is you would need to isolate the cube root. And so this minus 3 outside would need to go first by adding it. And then once you have isolated the cube root, be careful, that's not times 3. A lot of people write it as times 3 and then divide by 3. That's not what that says. That is a cube root. So to get rid of that, you cube. That's how you cancel out a cube root. Okay, and so after I cube both sides, I'm left with just an x plus 4 on the left. 3 cubed is 27. Last step, subtract 4 from both sides, so x equals 23. And so writing as the ordered pair, 23, 0. Okay, for this next one, once again, for the x-intercept, you are plugging in 0 for the y. Okay, so my whole function equals 0. So that leaves me with cube root of negative parenthesis x minus 3 parenthesis and then a plus 4 outside. And so we need to isolate the cube root, so subtract 4. And then now my entire expression is under the cube root. We are ready to cube both sides. Okay, and then remember, cube roots can equal negative. If I had square root equals negative, I would stop here and say no solution. But here we keep going. There's no domain restrictions. So that leaves me with a negative x minus 3 equals negative 64. Negative 4 cubed is negative 64. And then here we have a negative outside. You could distribute it, but it's easier just to go ahead and get rid of it. That's technically a negative 1. And so when you divide both sides by negative 1, you're left with x minus 3 equals positive 64. And then we can add 3 to both sides to get x equals 67. And so our x-intercept is 67, 0. All right, for this last example, we are writing an equation that is formed by reflecting our cube root parent function over the y-axis, okay? And then we are horizontally compressing by 1/2. Let's write that as a fraction. And then shifting it left 3 and up 11. Okay, and so for my equation, I would have my cube root, and reflecting across the y-axis puts the negative under the radical. Horizontally compressing it by 1/2 puts a scale factor of 2 under the radical. And so because I have a b value, I'm going to add parentheses to do the left 3. So x plus 3. And then lastly, the up 11 would be a plus 11 outside.